Alrighty, so now we are on to A.4, which is all about radicals and rational exponents. So we just had a lecture on integral exponents, so whole numbers. And so a rational number is now going to, has the word ratio in it, right? So we can think of ratio. And these are just fractions. Because fractional means something different. So we say rational. It's a ratio. Fraction, exponents. And we'll talk about what a radical is in a second. All right, so we are going to introduce some new vocab, right? So if a raised to the n power equals b, so I raised a to the n power and now it equals b, we call a the nth root of b. So that's an h. If it was a squared, we wouldn't say the second root, we would say the square root. These have like specific names. If it was a 3, a cubed equals b, then a is the cube root. So we would call b the cube of a, so a cubed is b. But how we would talk about b in context of, talking about a in the context of b, we go cube root. So the smaller number will be the cube root. Okay? So then if it was like a to the 4 equals b, we would say a is the fourth root. And that just means I need to raise a to the 4 to get to b. That's all that's telling me. So if n does not equal 0, because we're going to do 1 over n, and we can't divide by 0, then we say a raised to, or to the power of, 1 divided by n is the nth root of a. And we can write that as a to the 1 over n equals, sometimes you guys call this a square root symbol, but this is actually called a radical. And this little line right here is like a little pedestal to put a number. And that number corresponds with the denominator in the exponent of a. And then a is our base, so it still stays there. All right, so this symbol, that is what we call a radical. So it said radicals and rational exponents. So here's our rational exponent and here's our radical. Why is it called a radical? I literally just looked this up. It is derived from the Latin word for root. Is radix. So then it somehow got into radical. All right. So fun fact for you. So if n is 2, we just a square root. We would just write, like, instead of doing 2, we would write just a square root. So it's kind of just assumed. But if it's a cube root, 3, or any other number, it's n. And there's an assumption that we have that n is a whole number. So n is an integer in this situation. We're talking about 1 over a whole number. So not 1 over 2.3, okay? So I just want usually this to be a whole number, okay? So if we want to solve these examples, I have 16 to the 1 over 4. I can rewrite that as the fourth root of 16. And this is obviously, you can put this in your calculator, but obviously that's not the point of this. Like I've kind of mentioned before, it's like going to the gym and just using no weights at all. You're not really like beefing up your brain muscle if you use a calculator. All right. So 16th, the fourth root of 16. So this asks, what can I raise? Like what number? Oh my God, there's a fly. What number can I raise to the 4th power to get 16? So I know 16 is 4 squared, and I also know that 4 is 2 squared. So this is going to be, so 16 is going to be 2 to the 4th, which answers my question, that the 4th root would just be 2. Okay, so those are kind of ones that you're expected to know. Usually 2 to the maybe 5th, up to 3 cubed, usually at least from 1 to 4, knowing at least the cube of them so that you can go back and use the cube root. Nothing that I give you will be that difficult, and I think you, since it's open book, open note, you can use your calculators as well. But if you're just doing this mentally really quickly. So now for 2, it's 64 to the 1/3. So the cube root of 64, 64 is a tough one because it has a lot of different ones. Excuse me. It's an even number, so it's not going to be 3. 6 plus 4 is 10. So if we think about 4 times 4 is 16, and then 16 times 4, and that will give you 64. So the cube root of 64 is 4, because 4 cubed is 64. Okay. And then the square root of 16, we saw right here that this is just going to be 4. And let me put little boxes around these. Okay. Oopsies. So I've actually kind of already talked about this, but what is a rational number? You saw earlier how I used z for the integers. You're like, where did they get z from? That doesn't make sense. Well, guess what the rationals are? It's a q. So it makes even less sense. So the rational numbers. If you ever learned, like, you have real numbers, which is r, that one makes sense. Rational numbers, integers, natural numbers. I think that's it. And then there's complex and imaginary, but we don't talk about those. So like this hierarchy of numbers. So rational numbers are ratios. So they are ratios. If my alarm goes off in the kitchen, it means my banana bread needs to be checked. So I might have to like pause and come back in a little bit. You won't miss any time. So the ratios. So 1/2, 3/4, 100 over 7, or so 1,000 over 7, but also 2 over 1, which is just 2. So integers are also, or whole numbers are also rational numbers because everything is technically over 1. And we talk about them in terms of the fraction form instead of a decimal, because not every decimal is a rational number. Like pi. I can estimate it with like 22 over 7 or 3 or something. Probably 7. But that's only estimate. So there are numbers that I cannot represent in a fraction. AKA fractions. All right. So some of the properties that we learned in A3, right? The properties of exponents, we can define rational exponents. So we just talked about the 1 over n case. Now what if it's just a random number over another random number? So we would say like a m divided by n. Okay. Well, I can view that as a to the m to the 1 over n, or I can think about it as a to the 1 over n raised to the m power. And then I can even use a root, so something like this to the a to the m, and that would be it. Oh, my banana bread. Okay, be right back. Where's my pause button? Okay, I'm back. That's great. Whee. And then if I write a to the 1 over n in this third case as a root, a to the n. You will need to be careful about when we take even roots. We'll talk about that in a second. Because these two things might not necessarily be equal all the time. So think about a square root and how that can affect how many answers I get back out. Okay, so we'll do some examples and you'll understand what I'm talking about. So especially when it's negatives. Where is my cheat sheet? There we go. So I think it's best to take the root first and make the number smaller, and then take the power, the numerator of the exponent afterwards, because I don't really want to take the cube root of 8 squared. That sounds very hard. I want to square the cube root of 8. So I'm going to write this as parentheses tell us what to do first. So we'll do that 1 over 3 and then squared. So -8 is my base here. So what if 2 cubed is 8, then -2 times -2 times -2, I have that extra negative left over because 2 of them cross out. So right, do you see that? The cube root of -8 is going to be -2. So then -2 squared, -2 times -2, that's just 4. All right. And if you do it the other way, you should get the same answer. If I square it, I'll get a positive 64, and the cube root of 64 we just saw is 4. Okay. So 9 to the 3/2. Again, I don't want to try to find out what the square root of 9 cubed is. I don't even have to find out what 9 cubed is. Hard. It's 729. But let's take the square root first. I didn't write this how I wanted to. 9 to the 1/2, and then again to the third. I guess I didn't need that extra parenthesis. All right, so what's the square root of 9? It's 3 or -3, right? So if I do -3 times -3, that also is 9. So the way we write that is plus or minus 3 cubed. And then, so basically it's either 3 cubed or -3 cubed. And they aren't the same because odd powers, so 3, 5, 7, 9, will give me an leftover negative. So it's either going to be plus or minus 3 cubed is 9, 27. So plus or minus 27. Okay. Alrighty. So now I have 1 divided by 32 to the power of -3 over 5. Excuse me. So I think the first thing that we should deal with is that negative. So if I have a negative exponent, I want to flip my base, right? So remember that a to the -n is 1 over a to the n. So now I have like 1 over a to the -n. So this would distribute to each thing, but 1 raised to any power is just 1. So that negative in turn will just flip my fraction. So this is going to be equal to 32 to the positive. I brought this up, and then basically there's a 1 on the bottom, but we don't need to write that. It's like, what's the word called? I forget. Anyways, to the 3/5. So now a positive one. I see a lot of times people will flip the radical exponent, not radical exponent, rational exponent instead of flipping the base. If it's a negative exponent, it affects the base. Well, the exponent always affects the base, but it flips the base, not the exponent. Okay. So again, let's do our root first because we got 32 squared and I'm trying to find the 5th root of that. No, thank you. But since we know a few things, I know that 2 to the 4 is 16 and 32 is 2 times 16. So that's another 2. So the 5th root of 32 is just 2. And then I want to cube 2. Miss Kinsey, why didn't you do plus or minus 2? Because this is in what I would call an odd root. So the denominator there is 5. That's an odd number. Those are your friend because they let negatives and positives slide through, and that's the only option. But if it's an even root, if it was like square root, not cube root, 4th root, 8th root, 6th root, 100th root, that's an even number. Those you'll need plus or minus because the property of an even is that it pairs up into 2s. So every negative number pairs up with another negative number and their negatives cancel out. So you'll always get a positive number when you raise something to an even power. So when you're taking an even root, you can also have the chance of it being a negative root, negative base, so like -2 or something. But this case, since I'm doing the 5th root, it's only 2. And then 2 raised to the 3, 2 times 2 is 4, 4 times 2 is 8. Okay. I think 8 is such a beautiful number. Email me your favorite number. That'd be fun. Okay, cool. I'm forgetting to box my numbers. Yee. Okay, cool. So if you're okay with this, we're gonna move on. If you're not, maybe rewatch this or come to office hours or email me, okay? So now we did practice with numbers and we then worked with like fractions and weirder different versions of numbers. And now we're gonna move on to expanding what we've worked on to working with variables. So A, B, X, Y, and so on, right? So we're asked to simplify the following expressions. So remember, simplifying means I want to make it as small as possible. And by small, I mean number times variable to a number times the other variable to a number. And I really only want positive exponents, okay? So in number 1, my bases are the same. So what are my exponents going to do? What are they going to do? Add, that's right. I feel like Dora the Explorer. Where in the map are we going? I promise I'm just trying to make asynchronous online summer math fun, which sounds so hard and it is. I forgot my water bottle at the gym today. Never been so dehydrated in my life. All right. So, if you skipped over our pre-algebra review and you forgot how to add fractions, no worries, because this one's pretty easy. Since the denominators match, I can just add the numerators. So I get A to the 8/3. And I would rather see a fraction rather than, I think this is called an improper fraction. And I think that is really offensive to fractions everywhere. And I will not stand for that slander because it's kind of what we talked about earlier. An improper fraction is when the denominator is bigger than the numerator. So it's like writing 8/3 instead of 2 2/3, because of what we just talked about of separating it by taking a root and then raising it to the power. It's a lot easier to see that instead of being like, okay, 2 2/3. Do I like what do I? These obviously are, but they're not multiplied by each other. They're added to like confusing. So write it like that, okay? So I'm gonna box it. Um, okay, cool. So that was number one. Number two, a little bit more difficult. This is kind of also still practicing and harping on those exponential properties that we talked about last time. Okay. So for a cubed times b to the fourth, that whole quantity raised to the 3/2. So what we're gonna do is distribute that exponent to each term. Factor, excuse me. Terms are separated by addition. Factors are separated by multiplication. So this will be 4 to the 3/2 times a cubed to the 3/2 times b4 to the 3/2. And then if we focus on 4 to the 3/2, that'll be the square root of 4 cubed times, and then when it comes to variables, I can't even take the root of a, so I'm not going to separate them. This will be like a 3 times 3/2 and b 4 times 3/2 equal. These are all equal. The square root of 4 is, yes, it's 2, but what else is it? -2. Good job. All right. And then multiplying like 4 times something, remember these whole integers are just like basically over 1, and we multiply fractions across. It's a really nice thing about them. So this will be a to the 9/2 and b to the 12/2. All right. Whee. And then -2 cubed. Oh, sorry, that is not -2. It is plus or minus. Um, so this will be plus or minus 8. A to the 9/2, and b, if it gives you a whole number, I would just take it. Um, if it's not a whole number, leave it as an improper fraction. So I wouldn't leave 12/2. I would just make it 6. Okay. And that is all she wrote. And that's good. In the beginning, if you forget your negative, I'm not going to take off points, but on the exams, I will. On in WebAssign, it'll be like, please give me your answers in a comma delimited, whatever, something comma separated list. There we go. So you would write like 8, a to the 9th, b to the 6th, comma, -8th, a to blah, blah, blah. It doesn't understand plus or minus. There's no symbol for that, which I think is silly. So you have to do it twice. Okay. All right, cool. So now number 3, I have 2 square root of x times 3 cube root of x. It's hard to talk about radicals. So let's just make everything a nice, beautiful exponent. So these things aren't going to distribute to everyone. Like 2 isn't going to go to 3 and then to the cube root of x. Then I'm just like multiplying multiple 2's, and I can't do that. Just 1 2 involved. So this is like saying 2 times 3 times x to the 1/2. Remember, if there's nothing in that radical, we assume it's just a square root. That's a big thing in mathematics, is if the one number or base becomes so normalized, they just drop that number. And we'll see that later on. Log base 10 is just called log. They just drop the 10 because it's used so much. And then x to the 1/3. Okay, So this is going to be 6. 2 times 3 is 6. And then x to the 1/2 plus 1/3. This is not fractions working nice. So if you want to go over here and be like, oh, okay, 1/2. Plus 1/3. What do I need so that I can combine these fractions? I need a common denominator. So I can say this is like, or your best bet is multiplying the denominators together. So 2 times 3 is 6, so that would be my denominator. So to get 1/2 to be the denominator to be 6, I'm going to multiply it by the fancy one that is 3/3. And to get 1/3 to have a denominator of 6, I'm going to multiply it by a fancy one, which looks like 2 divided by 2. All right. And then I'm going to have 3/6 plus 2/6. And you can clearly see that this is still 1/2 and that's still 1/3. I've just beefed them up a little bit so that I can move them together. And then this is just going to be 5/6. So then I can come over here and say that this is 6x to the 5/6. Okay. If the problem ever wants you to write in radicals or rational exponents specifically, one or the other, it'll state that. If not, free will. But usually writing it in rational exponents is more than fine. The plus or minus is the tricky part. Okay, cool. Number 4 is one of my favorite problems. Pro tip, if I say something is my favorite problem, it will show up on your exam. I'm just gonna be flat out and say it because some students still don't get it. It's my favorite problem. I love to show it to you over and over again, okay? So you will see this problem again. All right, in some form, right? I can't give you the same exact problem, but whatever, okay? So let's make things in radicals into rational exponents, okay? So if you want to do it one at a time, that's totally fine. So let's do this first square root. So this would equal x square root of x to the 1/2. And then that other square root of x would then again turn into x to the 1/2. And you don't need to add these extra parentheses, but sometimes it's just nice. Okay. And then PEMDAS. So parentheses, we work from the inside out like an onion, go through layers. So this is x, that's like x to the 1. So bases are the same, exponents add, so 1 plus 1/2. Really quickly, that's 3/2. And then I still have this on the outside. Whee. So then those will multiply to be 3/2 times 1/2, which will give me a grand total of 3/4. Oh, sorry, x to the 3/4. All right. And like I've kind of said before, if these examples or you want some more examples, go to your homework and check those out. I would suggest first working on the web assigned one since you do get 100 tries on those, and then move on to the written homework, which is part B. All right, so we're done with this section for today, and I think this is all that's supposed to be done for June 22nd. So see you guys later.